Start okay now? Yeah, what were we talking about last time? We were talking about nuclear spin and the associated magnetism. Okay, so what does this mean? This means that we have talked about spin, Hannah, and we are familiar with spin, and we know that this is a property of particles. And when we are talking about the nucleus, we know that the nucleus is composed of the nucleons, and these nucleons, like the protons and the neutrons themselves, just like the electrons, they do have a spin property. But then there are different scenarios that we studied depending upon the number of nucleons. It is possible that for, let us say, for even nucleons, that they cancel out the spins of their neighboring particles, and as a result you do not have a resultant spin. So, we did talk about the fact that at the end of the day the nucleus can have a spin property, but then the nucleus will behave as a single entity. Okay. It will manifest itself as a single entity as a result of the internal spins of its constituent nucleons. And then we talked about different examples. We talked about, for example, the hydrogen nucleus, right, and we talked about the fact that in the hydrogen nucleus we have, in the nitrogen nucleus we have a odd number of protons, right, and therefore it is a nucleus that would show a spin. So, we continue from there, and so just like the nitrogen, there are a number of nuclei that can have this property. For example, hydrogen 1 or carbon 13 or nitrogen 14. So, these are some examples of nuclei that have this property. Another thing you will notice and that these nuclei are also present in the human body, and therefore this is these are nuclei that are present in biological matter, and hence you have this MRI and NMR signal is based on this property. Okay. So, the simplest nucleus is the hydrogen nucleus, and if you like, we know that hydrogen is very abundant in the human body. So, therefore, hydrogen nuclei exhibit this property, and this can be detected, and the nucleus can show a net spin. So, the net spin is greater than 0 and it does not cancel, and we can have a resultant nuclear spin, and as a result of the nuclear spin we can have an associated magnetism. Okay. Now, another thing that we are aware of is the fact that whenever you have a charged particle, the charged particle moves, it can have a magnetic effect, right. It will create a magnetic field, and as we know that a hydrogen nucleus can be considered as a charged particle, because a hydrogen nucleus basically is a proton, right, and therefore it will behave as a charged particle, and it will show you this will behave similar to a positive, let us say, charged particle, and as a result you will have the spin property and the associated magnetism with it, and the associated magnetic field, right. Okay, so let us stop this here. Now, we will go to another property, which is the nuclear angular momentum. And parity. So, if we look at page 34, like I said, we are using chapter number 2 as a reference. Okay. So, it is not again students who have not studied this as a course, as an independent course, you do not have to worry about it, because we will just refer to the let us say symbols or equations whenever we need them or whenever we use them. It is not like a part of your examination. Okay. And I mean chapter 2 is a summary of some quantum mechanical concepts and formulas. So, we will be using them from time to time, but then again you do not have to worry or get scared okay, there is quantum mechanics in this, okay, because some properties do relate to quantum mechanical concepts and this. You do not have to derive those equations or go really deep into them, you just have to use them from time to time, and that is what we are doing. Okay. So, in classical physics we know that L is the angular momentum of a particle. Okay, and we know that P is the normal momentum of a particle. And we know that R is a position vector. And we have this formula which is R cross P. So, I am trying to relate this concept to what we already know, right. And quantum number is again another concept that we are familiar with and that we use from time to time. So, what is a quantum number?
Set of numbers that can explain certain quantum properties.
Yes. So, we have a set of numbers, and these are related to the physical properties of a system such as angular momentum and so on, and they have discrete values. So, one of the important things that we learned from quantum mechanics or quantum physics is the discreteness of some values, the quantization concept, right. So, okay, so they can have particular values, and this property is said to be the property of quantization. Okay. So, for example, we can have the Bohr's theory of an electron. You know, again the Bohr's theory of an electron says that an electron can only occupy an orbit for which it has a certain angular momentum. Again, the Bohr's, this is not about the nucleus, but we are just referring to previous knowledge that we have about physics. So, you have been studying this. So, according to Bohr's theory, an electron can only occupy an orbit for which its angular momentum is nh over 2 pi. So, what is important here is n is an integer, right. So, this is the concept of quantization. So, it can have the property of angular momentum, and this property is quantized, and therefore, n is known as a quantum number that gives its possible values. Okay. So, this is a quantum number. So, quantum numbers are also used to define the properties of elementary particles. So, for example, the electron is an elementary particle, and it has a property of the spin. So, it can exist in specified energy states depending on whether the spin is parallel or antiparallel to any reference that is chosen. So, normally the two states of the electron spin are considered as plus half and minus half. So, similarly, other properties may be characterized by quantum numbers, and so therefore, we have these symbols. Okay. इसको बंद करो.